Hey guys, welcome back. So this is Unit 11, Sequences and Series. We're just going to cover just the basics of what sequences and series are and the idea of sigma notation. This video will refer to using your calculator in a certain way. So make sure you're referring to the TRE4 graphing calculator video on how to use sigma notation with your graphing calculator. So sequences in mathematics is just simply an ordered list of numbers. Each number in the sequence is a term. And when we talk about finite versus infinite sequences, finite, there is as the name suggests, a finite number of terms. There's 7 terms in this, 12 terms, 8 terms, whatever it's supposed to be. Infinite goes on forever, obviously. And then sometimes you can actually write a formula for the sequence, or sometimes a formula is provided for a particular sequence. The formula is going to be based on the variable n. You can convert your calculator mode into sequence mode. Again, I'll show how that works. We go over the sigma notation stuff there, but it's just simply another variable. But in general, the formula that we use to write and describe a sequence is called the explicit formula. There's two ones we'll talk about, explicit and recursive. So this is not a formula, it's just simply a list of numbers. So we're trying to recognize what the pattern is. So looking at 2, 3, 5, 7, 11. So depending upon the scenario here, you might want to look at, okay, how are the numbers increasing? So we're going up +1, +2, +2, +4. It's not really a consistent pattern there with the numbers, where if it was like, up +1, +2, +3, +4, then it's like, okay, they're increasing and the amount of increase is increasing each time. Awesome. That's not what's happening here. So we look at okay, what type of numbers do we have? 2, 3, 5, 7, 11. Well, those all look like prime numbers. In fact, they are prime numbers. They are the first 5 prime numbers we have. So 2 is the only even prime number, and after that it's all odds. 3, 5, 7, we skip 9 because it's divisible by 3, then 11. So our next 4, well, after 11 we would have 13. And then 15 is divisible by 5, so then we have 17. And then we have 19. And then 21 is divisible by 3, so then we would have 23. So look for types of numbers. Maybe they're prime numbers. Maybe they're even numbers. Maybe they're perfect squares, perfect cubes. Maybe it's a number that's 2 less than a perfect square. We'll just look for what could connect these numbers in some way. Now the explicit formula is something like this right here. an equals 2n times -1 to the nth power. So if we want to find the first 4 terms, we're going to fill in n equals 1, 2, 3, and then 4 into this equation. So we would say a1 is 2 times 1, and then -1 to the first power, which is -2. a2 is 2 times 2 times -1 to the second power, which is 4. a3 would be 2 times 3, -1 to the third power, which is a -6. And then a4 would be 2 times 4, -1 to the fourth power, which is +8. And then for future reference, this thing right here, the -1 to the nth power, we use that to show that if we want our pattern to alternate positive, negative throughout the question. That's the only purpose, because -1 to odd powers stays negative, -1 to even powers becomes positive, so it doesn't affect the actual number in terms of 2, 4, 6, and 8. It's like getting that versus other numbers. It just affects whether it's positive or negative. Now, in addition to explicit formulas, we have what's called recursive formulas. So recursive formulas are ones where they're defined by, you're given either 1, typically 1, but sometimes you're given the first 2 terms, and you're asked to describe all future terms based on those 2. A common recursive formula is or at least classic one, is your Fibonacci sequence, which you start with 1, 1 for the first numbers, and all other numbers after are the sum of the previous 2. So you had 1, 1, and then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and so on down the list. That's a classic recursive formula. So here, they tell us a1 is 1, so we're starting with the first term. And they tell us an is an minus 1 plus 2n minus 1. So this is the next term. This is the previous term. So if I want to find a2, well, that would be a1 plus 2 times 2 minus 1. a1 is 1, so it's 1 plus 4 minus 1, we get a 4. So then a3 would be a2 plus 2 times 3 minus 1. So we'd have 4 plus 6 minus 1, which is 9. A4 would be A3 plus 2 times 4 minus 1. So it'd be 9 plus 8 minus 1, which is 16. And I only wanted the first 4, so since even though they gave us A1, we don't need to find 4 more. They already have that for us. And you'll see here we're going 1, 4, 9, 16. This is the sequence of perfect squares. So this recursively defined formula is describing how we get all perfect squares. So just make sure you're very careful with that whole an minus 1 bit. It's the previous term that you just found. You're using it to get to everything else. So these can be a little bit slower. If I want to find, like, the 7th term in a recursively defined sequence, I have to find all 6 terms previous to that in order to get to it. Whereas in explicit form, I just can plug in 7, n for 7, 7 for n, there we go, and they'll give us my answer right off the bat. Now, this will be important for more so when we get into the idea of your calculus class. If you're taking AP Calculus BC level, there's going to be a lot of conversation about convergent versus divergent series and that. So this is going to be kind of like doing a little introduction to that idea. So this is only based off an infinite sequence. A sequence is converging to a number or not, or converging to a number or not, based off what's happening with, as n is getting larger, are we approaching a certain number? And if we're getting closer and closer to 1, let's say we go from let's say we get 0.1, then we have 0.6, and then we have 0.8, and then 0.9, and then 0.95, and then 0.97, and then 0.99, and then 0.999. You're clearly approaching 1. We're getting closer and closer to the value of 1. Each new number, the difference between that and the previous number is smaller. Whereas it's going to diverge is as we're getting larger and larger in our sequence, the sequence is either getting infinitely large or infinitely small, or it's going back and forth between two numbers. Maybe it's going positive, negative, positive, negative, positive, negative. So if, for example, we had something like this. Let's say we had negative 8, and then positive 10, and then negative 12, and then positive 14. And then we had negative 16, positive 18, negative 20, positive 22. You can see you're getting further and further apart. This is going to diverge. Do be careful the whole back and forth positive and negative, because if it was going negative 0.5, positive 0.4, negative 0.3, positive 0.2, they are going back and forth, but they're getting closer and closer to 0 as they do so. So just be careful with the oscillating back and forth between positive and negatives. So an easy way to tell if the sequence is converging or diverging, we're just going to take a look at a couple numbers in here. So we're going to start with A1. So A1, negative 3 times 1 plus 12, we get 9. A2, negative 3 times 2 plus 12, we get 6. A3, we have negative 3 times 3 plus 12, we get positive 3. A4, negative 3 times 4 plus 12, we get 0. And that's really kind of enough of a look there. If we need to see a little bit more, you'd go a little bit further. But you can see that there is the amount of change between each of these numbers in the sequence, 9 to 6 to 3 to 0, is not changing. We're not getting closer together. We're not getting further apart, really. We're just staying consistently decreasing by 3 each and every time. So that means this is going to diverge. Converging, the numbers need to get closer and closer together. So it had to have been 9 to 6, 6 to 4, 3 to 2 kind of thing, where they're getting closer and closer together as you go further and further. That'd be the idea of converging. So that one's divergence. If you want to look more at converging, that might be more along the lines of something like, let's see. Make something up kind of on the spot. Let's say we have something like this. AN equals, let's say, 5 over n. So here we have A1 equals 5 over 1, which is 5. A2 would be 5 over 2, which is 2.5. A3 would be 5 over 3, which is 1.6 repeating. A4 would be 5 over 4, which is 1.25. So you can see the numbers are getting smaller and smaller, but they're also getting closer and closer together. Each new change, the difference between them is going to be getting smaller. So this will converge. And again, I'll kind of show you on the calculator as well, the whole converging versus diverging, how you can kind of see that with the table of values going forward. Now, a series. So a series is the summation of all the terms in the sequence. So like sequences, the series can be finite or infinite. Typically, if it's going to be finite, That's a little bit easier to figure out. We'll typically call that a partial sum, where we're like, okay, so this series, sequence, let's find the sum of the first 10 terms in the sequence. So we kind of make it finite, Sn, so we'd be finding S10 for that situation right there. So here, if we want to find our fourth partial sum here of an equals negative 2 to the nth power plus 3, we'd have a1 negative 2 to the first plus 3, which is 1. a2 is negative 2 squared plus 3, which is 7. a3 is negative 2 cubed plus 3, which is negative 5. And a4 is negative 2 to the fourth plus 3, which is 19. So S4 would just be a1 plus a2 plus a3 plus a4. So it would be 1 plus 7 minus 5 plus 19. And we get that to be 22. So for this particular sequence, the sum is 22. Again, these have to be kind of based off our partial sums. It has to be based off a finite thing, because for the most part, a lot of sequences, if they're infinite, if the series is infinite, it's not going to give us a value, a sum, unless it converges. And that's where, again, the whole converging versus diverging comes back into play. Now, another way, and a little more useful way of writing out the summation is using the sigma notation. So this is where we have our uppercase letter sigma, signify this series right here. So sigma, summation, n equals 1 to k of our series an is going to be a1 plus a2 plus a3 all the way up to ak. AK could be infinity if it's an infinite series. It also could be like, 7 if I only want to find the first 7. But the bottom part does not have to be n equals 1. I could go from what is the sum of the third through the 7th term. So it'd be n equals 3 to 7 there. So this is the part where you're going to be using I'll show you how to do it by hand, but also this is going to be more often now you're going to use a calculator for this kind of situation. And that's where, again, the TID4 calculator video will show you how to type this information into that. So we'll find our first term, a1, 4 times 1 minus 3, which is 1. a2, 4 times 2 minus 3, which is 5. a3, 4 times 3 minus 3, 9. a4, 4 times 4 minus 3, which is 13. And then a5, 4 times 5 minus 3, which is 17. So if we add all those up, we're going to get a value of 45. So that'd be the sum of that. And we're going to deal with some more interesting, complicated summations as we go further through this unit, so make sure you are comfortable using the calculator for that part. Because for certain situations, otherwise you're doing it by hand, and that can get a little tedious and not exactly in your best interest to complete. All right, so that's a little just intro to our sequences and series. We'll get into the different types of sequences and series as we go through this, as well as its different uses. So I'll see you guys next time for those future videos.